Today, we're going to talk about machine learning with heterogeneous graph. So far we have been talking about machine learning with simple graphs where there's no type information inside the graph. So nodes and edges, they are treated equally, they are homogeneous. So today we're going to cover a more generic or more general family of graphs where we can further consider the category or types of different nodes and edges. And we call this a heterogeneous graph. So this will be the topic for today's lecture. And a quick announcement, we have the project proposal due today. So if you haven't finalized your proposal, it should be 2-page. Please finish today. So let's get to the technical content for today. Today we'll be talking about heterogeneous graph. So far we have been handling graphs with only one edge or node type, right? So we just introduce there are nodes and edges in the network without further describing the types of these nodes and edges. However, there are some very good reasons that in reality, the graphs may come with types. So how do we handle these graphs where there could be multiple types of nodes and multiple types of edges? And this is also known as heterogeneous graph. Specifically, we'll today cover 3 different methods that can perform machine learning with heterogeneous graph. The focus today will be the relational GCNs, which is the first and the most widely used method that can be used to learn from heterogeneous graphs. We'll then cover a recent state-of-the-art method called heterogeneous graph transformer, which basically extends the idea we have learned, the graph attention network, from homogeneous graphs to heterogeneous graphs. And lastly, we'll start some discussions regarding how can we define a design space for heterogeneous GNs. So if you remember a few lectures back, we have talked about a general perspective for GNs, and that was over homogeneous graph without any type information. So today we're going to use some slides to discuss how that framework can be extended to heterogeneous graphs as well. So the focus today will be the relational GCNs. So let's first motivate why do we want to study heterogeneous graph, why this notion is even useful. Earlier we have shown that we want to study graph because it describes entities and their relationships. In practice, these entities, or we call nodes, could have different types. Let's say could be like a citation network among different research papers and different authors. And for this graph, we can actually define 2 types of different nodes. So the red node could capture the papers, and the blue node can represent the authors. So you see, because we treat, usually we will treat papers and authors differently. Say we have some paper-specific attributes like the number of pages, the topic of the paper, and we can have some other attributes for the authors, like maybe the nationality of the author, which school the author belongs to. Because these different nodes could have different attributes, it would be natural that we can represent them as 2 separate types, and then we want to represent such types in the network. Another example is the case where we have different types of edges. And this could be also useful in our citation network. So the first type could be one paper cite another paper. Another type of connection could be one paper like another paper, so they are similar. So similarly, because there could be different types of connections and interactions in the network, we may want to represent them with different edge types. And then we can make the case even more complicated. So given a network, it can both have different types of nodes and different types of edges. Still reusing our example, we could have 2 types of nodes in the citation networks, the papers and authors, and we can additionally have 2 types of edges that are the citation relationship and the similarity relationship. So altogether, both nodes and edge types can exist in the same network. And you can already see this heterogeneous graph can go very complex. So there are tons of combinations of like how many nodes and how many edges you can consider in this heterogeneous graph. So how do we efficiently capture this complex type relationship in a heterogeneous graph? So the key idea throughout this lecture will be the concept of relation. So inside a relation, it will be a tuple of 3 elements. We talk about the starting node, the edge, and the end node. So let's say given this red node, it will connect with this blue node through an edge, this green edge. And we can use this tuple to succinctly capture the complex relationship or interactions between a pair of nodes. So we capture the type of the starting node, we capture the type of the edge, and then the type of the ending node. So let's make this more concrete. In this example, in total, we could have 8 different relation types, because we talk about there are 2 different node types and 2 different edge types. And because we are considering this tuple, and each element of the tuple, you have 2 choices. So altogether, you could have 8 different potential relation types, from paper-side paper, paper-like paper, up to an author-side paper and an author-like paper. So overall, there could be 8 different relation types. And in practice, and in the remaining of this lecture, we will use this relation type to describe an edge. So this is as opposed to we directly use the edge type to represent an edge. The reason is that, as we can see, this relation type is more expressive, and it can cover the better captures the interactions between a pair of nodes and edges. Any questions so far? Question?
I guess could an edge be both? Could 2 vectors be similar but also side each other?
So you mean one edge containing 2 types? Yeah, that's a good question. So in our setting, we do not consider this so-called multi-graph. So one edge like represent both types. One way to represent that information is that we can add 2 different edges here. So let's say like one paper like another paper, and another paper side, the same paper also side the paper. So we can use 2 separate edges to represent, suppose 2 relations exist. Okay, so we'll talk about this relation type throughout this lecture. So with this definition, we can now formally describe what is really a heterogeneous graph. First, a disclaimer. There are multiple ways to define a heterogeneous graph, and you may read different definitions either in blogs or research papers. But all of them serve the purpose of describing a graph which has multiple node types and multiple edge types. So we'll pick one particular way to define heterogeneous graph. You have V, R, T, and E, 4 components to describe a heterogeneous graph. First, we have nodes with different node type. So Vi is a particular node inside a set of nodes, and each node will be described with a particular type. And to get the type of given node, we have this transformation T that basically tells us what is the type of a given node Vi. We then additionally define the relations within this heterogeneous graph. And as we have motivated, instead of using one single edge to represent this relation, we use a tuple with 3 elements: the starting node Vi, the edge E, and the end node Vj. And out of all the possible relations, we'll use a set R to represent all the relations. And finally, we define this edge type E that belongs to, I think this is a typo. We reuse the notation R here. this should really be E. But basically, we also define an edge type that belongs to a set of different edges. Overall, this definition all about is to say we have a graph and we associate different types for each node and different types for each relation tuple. Question?
Sorry, a little bit confusing about the notation. So you said relations with relations type this specific tuple that belongs to R, but then later you also said the edge type E also belongs in R?
Yeah. As I said, this should be a typo. I believe this should be E. So small e means that a particular edge type, let's say site or like, and the capital E means the set of all possible edge types. I think these are just tells us all the possible tuples inside the heterogeneous graph. Yeah, I'll make sure to correct after the lecture. So now we have defined heterogeneous graph, and you may wonder that this notation seems to be pretty complex, and are there like a real-world use cases of using heterogeneous graph? And the answer is yes. So actually, there are tons of real-world graphs that should actually be represented as heterogeneous graphs. We will visit several examples. The first is a so-called biomedical knowledge graph, and this can constantly arise in biomedical applications. In this case, you may see there are different nodes with different colors, and that means that the nodes belongs to different types. For example, we can have like a example node, this migraine. This is like one particular node, and this belongs to the red type of node, which is a disease node. And then we can define a particular relationships between two blue nodes, which are the drug node. And then there are other examples of node types and edge types. So you see that in this biomedical knowledge graph, you can define different types of nodes and then capture their relationships. Another example is this event graph, where say an airport SFO is one type of node. We can capture the relationship between a specific flight that originates from this airport. And in this case, we can have a node type of flight and then an edge type of destination. So in a lot of real scenarios, you can describe a graph together with the type of the nodes and edges. Question?
Is there any way to express the different level of causal relationship? For example, in the biomedical knowledge graph, there will be a causal relationship based on the microarray, which is weak causal relationship, and then based on the meta-analysis, which is a strong relationship. Is there any way to express this level of relationship?
Mm-hmm. So the question is that can we represent those like a hierarchical structure of the relationships? So in other words, can we even say build a like the connectivity between the relationships? Yeah, I think that is doable, although we didn't talk about it in this lecture. So in that sense, we are further connecting. We can further connecting the edge types together. So we can use construct a separate graph that tells about the hierarchy of different edge type, let's say, and that can be used in a company with a different heterogeneous graph. But with our current representation, we just assume all the types they are like treated equally. So we have maybe 10 node type and 10 edge types, but we can additionally construct a graph that link different node and edge types together. Yeah, but that's a good question. Let's see more concrete real examples of heterogeneous graph. Another very common use case is this e-commerce graph. For example, for recommender systems, we will have different users, different items, and different queries, and they can be represented as 3 different types of nodes. And then we will represent their interactions as the edges. But here, the edges can also take different types. So we can define the relationship of search, the interaction type of click, and guide. So there are also 3 and even more types of interactions within this e-commerce graph. So this is like a very widely used scenario in industry when people want to build like a recommender systems that can associate different user item queries together. And one more example, and we'll also talk about a benchmark dataset from this example. We can further build an academic graph, so including different authors nodes, venue nodes, and field nodes. So there are 3 types of fields, and then we can also define 3 types of interactions. That is, for example, an author publish a paper belongs to a field, and there are also citation relationships between these different types of nodes. So this is yet another good example of heterogeneous graph. And based on this formulation of graph, we will later talk about a benchmark dataset that is the most widely used benchmark for heterogeneous graph called Microsoft Academic Graph that basically construct this like a author venue field, like a heterogeneous graph over all the open access research papers. And a lot of GM benchmarks are computed for that benchmark. So now we have defined what is a heterogeneous graph and seen a lot of real-world examples of heterogeneous graph. Before we jump into defining like a machine learning model to learn from heterogeneous graph, I want to spend 2 or 3 slides just to discuss, do we even need a heterogeneous graph? So indeed, there are a lot of cases you may find that there are type information associated with node and edges, but what we want to argue here is that instead, you can consider model that type information as a feature alternatively. So there are some very important practical decisions for you to consider before you want to formulate your problem as a heterogeneous graph. So our observation here is that instead of associated with node and edge with different types, we can instead consider them as different features. So one a simple example is that we can use an one-hot indicator to represent the types of nodes and edges as an additional features. For example, still using our example of academic network, for 2 types of nodes, author node and feature nodes and paper nodes, we can use a one-hot encoding 1-0 to represent each author node and feature 0-1 to represent each paper node. And even though we may have any additional attributes for authors and papers, suppose we append this additional indicator feature to these 2 types of nodes, then essentially we have injected this type information to the network. So in this case, you no longer need to directly represent the type information, but instead we can just use them as additional features. And similarly, suppose we have edge types, we can also treat edge types as edge features, and then consider learning from the edges with additional edge features. And under this perspective, we essentially reduce a heterogeneous graph into a standard or so-called homogeneous graph that we have discussed multiple lectures before. So are there cases when we really need a heterogeneous graph? So here I show 2 examples that I thought are pretty important to use heterogeneous graph, but you can consider more cases. The first case that we have good reason to use heterogeneous graph. In some cases, we may have a 4-dimensional feature for author nodes because there are, let's say, 4 distinctive attributes of a given author, and there could be a 5-dimensional feature for a paper node. Let's say we have 5 different attributes for the paper nodes. So in this case, suppose we just treat this type information as features, you may find an issue because now different nodes have different dimensions of input features. And if you recall, for any graph neural network, our assumption is to reuse the message computation across all the nodes. And now we face into an issue because right, the input feature for different nodes are different, but we want to share the same computational graph. And that could be a problem. Of course, like there are some workaround. Let's say we can map the feature into the same dimension, but still like there are cases where the input feature dimension mismatch. And in that case, we want to consider modeling these two types of nodes as a type rather than features. In another example, we may have like a prior knowledge or external knowledge saying that these different relation types should represent different types of interaction. Let's say we have like a graph built over different languages, and the tuple, the relation type between English translated into French and another relation type English translated into Chinese. These are two different relation types. And suppose we want to build a model to capture these two types of interactions, then this will require different models. So suppose we just treat this information as feature information, then we will reuse or share the same weights across all the edges. And that is kind of not what we expect. And in this particular case, it would be better that we model this information as a type as opposed to as a feature. So these are just some brainstorming ideas showing that what you should consider when you decide whether a feature or attribute should be considered as a type or considered as a feature. So here's like the final conclusion we have after the discussions. Ultimately, we know this heterogeneous graph is definitely a more expressive way to represent the interactions between entities because it can capture different types of interactions between the nodes and edges. However, this also comes with costs. So for heterogeneous graph, it will be more expensive in terms of the computation because now we have different types of interactions. And it's also more expensive in storage, either in terms of the fact that we want to store additional type information, and also that we most likely wouldn't be able to store everything into one single matrix, but different separate matrices for each type of information. So it's more expensive in storage as well. And additionally, the implementation, as you can imagine, for heterogeneous graph, it will be much more complex. So it definitely comes with cost. So our discussion here is to share some insight that there are many ways that we can convert a heterogeneous graph back to a standard graph that we have discussed in the previous lectures. That is so-called the homogeneous graph. But suppose you do want to model this complex and different types of interactions between the network, you should consider using heterogeneous graph instead. Okay, so now we have motivated the idea of heterogeneous graph. Next, we're going to introduce the machine learning model that can learn from heterogeneous graph. And particularly, we will talk about relational GCN as the first and most widely used method to learn from heterogeneous graphs. So as a recap, this is how we define so-called graph convolutional networks. For a homogeneous graph, we compute the message for each neighbor with a transformation W, and then we perform an aggregation across all the messages normalized by the degree of the input node. So it still falls under the message and aggregation function we talk about, and this is for for a homogeneous graph. In our discussion, we'll slightly extend like the definition of the graph. So instead of consider an undirected graph, we'll consider like a directed graph, just for the better illustration as you will see later. And then we can consider the simplest case where there's only one type of relation in this directed graph. And based on what we have defined for GCN, our goal is to define a computational graph that can generate the representation for a target node A. So this will be the computational graph for this particular directed graph. So we will look at A's neighbor B, C, and D, and B will have one neighbor C, and C has neighbors F and E, and D does not have any additional neighbors. So this is like the computational graph for a directed graph like this. So it's really nothing different from what we learned, except that now, because we define the input graph as directed, the message will only be passed along the direction of the edges. So recall that earlier, since there are no direction of the edges, the messages are essentially passed bidirectionally. So now this is passed directly. And we do not consider any additional type information here. This is the standard graph we have seen a lot of times before. So in this case, all the transformations are shared. So you can see that they are colored with the same color. So which means that we share the operation for all the nodes. So now let's consider the case of heterogeneous graphs. And in the case of heterogeneous graph, we could have different types of relation that we have motivated earlier. So in our example, we have 3 different types of relations, and the edges with the same relations, we color them with the same color. And additionally, this relation type, as we talk about, is really about a tuple of starting node, edge, and end node. And we want to simplify the notation, so we just use a single relation, say R1, to represent this full tuple of relationships. So this is our setting. So we want to, given this heterogeneous graph, we want to learn from it still using this graph convolutional neural network. So what are our ideas here? Because we know that there are different types of relations, our intuition is that instead of sharing the weights across all the nodes, now we'll have a different weight matrix for each different types of relations. For example, we have these 3 types of relations in this input heterogeneous graph. And based on what we have seen, we'll then define 3 different weight matrices. Each weight matrix is corresponding to one particular relation type. And we want to use these different weights to capture this different types of interactions for a network. So this is our idea and motivation of learning from heterogeneous graphs. So what does it mean in the computational graph is as follows. So we have the same computational graph structure. So like a node A still have B, C, D as the neighbors. B has C as the neighbors. So the structure of the computational graph does not change at all. The only thing that has changed is the weights of the neural networks. So remember that earlier, all the neural networks or the weights are in the gray color, which means that they are shared across all the nodes. Now, because we know there are different types of interaction, we will use different colors to represent different types of interactions. So let's see some example. Because we know the edge or the relation from node D to A is this blue R1 relation type. In this computational graph, we also make sure to use this blue weight to represent this particular relation type. And for example, here, A and C is transformed using this red weight. And we can see that the edge from C to A is indeed this red type of edge, R2. So this is our basic idea of how to repurpose a graph convolutional neural network for heterogeneous graph. We keep all the computational graph structure to be the same, except that we will now assign different weights for different types of nodes, different types of relation types. Any questions? Okay. So this is essentially the key idea of all the remaining discussion in this lecture. So we just use different weights or different instantiations of neural networks to capture different relation types. And we can think the same process in a slightly different way. So instead of considering a heterogeneous graph as one graph, we can consider it as n different graphs, where like one particular graph talks about the connectivity with respect to one relation type. So because we can have n different relation types, we can consider n different graphs, each connected with one particular relation type. And what we do is that can be considered as, instead of learning from one giant graph, we perform machine learning for n different relational graphs, each for each relation type. And because we know that there are n different graphs, we have defined n different set of ways to represent these different types of input graph. Question?
So this kind of approach would make a lot of sense if we're sure that all of the different labels for the edges are truly independent, right? Because we're basically saying each one of them is its own graph. But I guess in reality, this is kind of like a choice for real world data for us to make this kind of choice, and it makes sense to have 4 different labels, let's say, for edges. Is there a way for me to analyze these weight matrices so to know if there's actually a covariance between them or not? So basically saying, to help me choose whether I should do heterogeneous graphs or not, or how many in real world applications?
Yeah, that's a good question. So I think the question is also motivated by this observation, in the sense that we are curious, like how correlated are, what are the correlation between each type of relations. As far as I know, I don't have like a knowledge about like a very principal ways to detect like to what extent we should consider as a homogeneous graph or heterogeneous graph. But in practice, like I would suggest like you can try both methods and see which performs better. I think usually in practice, I would suggest you start with like treating this type information and features as we have motivated earlier, because it is much more easier to implement. And suppose the performance is not satisfiable, where you want to expect higher performance, then you can consider using heterogeneous graph. We haven't talked about the implementation of heterogeneous graph yet, but usually it is slightly more complex than a homogeneous graph. Okay, so this is another like a perspective of what we are doing here. So we learn like n different neural network for n different subgraph that are constructed from the same input graph. So now we're going to talk about the specific like a definition for a relational GCN. And this is really like nothing different from a standard GCN, except that we consider the type information, and we will use different weight matrices to represent different types. So this is the definition of our GCN. And you see that we still have a lot of things we're familiar with, right? So we use the weight matrix W to transform a given node. We'll perform an aggregation of over the neighbors of a given node. And we additionally perform an aggregation over a different relation type R. So we can still understand this equation through the 2 steps we have been talking about, message computation and aggregation. So now for a heterogeneous graph, the message computation is specific to a given edge type. So you can see there a subscript R says that this weight matrix is particular for one given relation type. So we will transform the input node based on the relation type we know, and then we can create like a message based on each of the relation type. And it is worth noting that we still consider like the weight that transform the node itself. So we talk about we want to have 2 parts of information, right? One part of information from the neighbors of a given node, another part from the node itself. So still we have this term that capture the transformation of the node itself. And then after computing these different types of interactions, we'll perform aggregation. And you can notice that instead of performing one summation in the standard GCN, now in this equation we have a double summation. This is because we first want to aggregate the messages within one relation type, as we have seen also in the homogeneous graph. But now, because we have R different types of relations, we want to additionally summing over different relation types. So this is like how the RGCN is defined over different relation types. So next, we're going to discuss like what are the the implications and the potential issues of this RGCN formulation. So in the end, we want to learn the different weight matrix for each type of the relations. So ultimately, we have this R different weight matrices, and each weight matrix has the complexity of D squared, which basically says we have the input dimension for each type of the node, given node type, and then we want to project it into the DL plus 1 to the next dimension for the next layer. So this is like the shape of a given weight matrices, and we want to have R different weight matrices. And you can observe that because inside like a heterogeneous graph, there can be tons of different relation types. So even there are, say, 2 node types and 2 edge types, as we have seen, we can potentially have 8 different relation types. So soon it will become overfitting will become an issue because you simply have defined so many different weight matrices to learn from. And this is an issue both in terms of overfitting and also from the cost of the computation. So next, we're going to discuss 2 practical methods that are widely used to alleviate this issue. Basically, we want to regularize the weight of WRL for each relation type to make the cost to be more affordable. The first approach is to use a block diagonal matrix to reduce the number of parameters for each weight matrix for each relation type. The second method is to do a basis decomposition, or also known as the dictionary learning, to reduce the effective number of parameters. And in practice, you can actually combine both methods to make the number of weights even smaller. So let's talk about the first approach to track the computational cost. So the insight is that we can make these trainable weights to be sparse. So one option to make this sparse is to formulate as a block diagonal weight matrix. So earlier, we have always assumed that any neural network transformation are a fully connected layer. So in the sense that the weight matrix is a dense matrix. So all the values are non-zero. And in this case, we want to reduce the number of parameters by making it to be block diagonal. So only this block diagonal entries are non-zero. The remaining entries are 0. So we can treat it as like a special type of sparse matrix. The limitation of this approach, suppose we want to use this block diagonal matrix, is that we will only consider the interactions between the nearby neurons or the dimension of the input. So in this case, only suppose we are computing over the first block diagonal entries, then only the node 1 and node 2, they will have interaction. But say the node 1, the dimension 1 and dimension 3, you wouldn't have any interaction because there are no ways to represent this like a remote connectivity. But indeed, this approach is effective in reducing the number of trainable parameters. So let's say we use B to represent this low-dimensional matrix. Then essentially, by using this block diagonal idea, we're reducing the number of parameters from D squared, roughly D squared, to D squared over B. So we essentially reduce the number of parameters by ratio of B. Another widely used approach is to share the weights across different edge types. and essentially reducing the trainable parameters. In this case, we have the idea of so-called basis decomposition or basis transformation. So instead of letting this weight matrix WR to be fully trainable, we can instead consider the following formulation. We have this another matrix VB to be like a so-called basis matrix, and then we will train a trainable vector ARB that kind of tells us the importance of the weights of different columns of this matrix VB. So essentially what we learn is only this ARB that tells us like how to linearly combine different columns of the weight matrix VB. And this way we can generate like a different weight matrix for different relation type, but without having to define R different weight matrices. So ultimately, to capture this relational-wise information, now we only need to learn this vector ARB, which only has a B number of scalars. So this can also significantly reduce the number of parameters. So now we have talked about the idea of RGCN and how to make the computation more tractable. Next, we're going to discuss some concrete applications, how to apply this RGCN to, say, node classification and link prediction that we have also seen in previous lectures. So first, for node classification, the approach of applying RGCN is quite similar to what we have seen earlier. So let's say we want to predict node A, which have k different classes. Then we're still using RGCN to generate the embedding for this node A. So we have this vector for node A, HAL, that represent the final layer of output for this node A. And then we'll compare our prediction with the ground truth and then perform the center back propagation. So this is very standard. We have seen this in homogeneous graph as well. What becomes more like a complicated is for link prediction. So recall that for link prediction itself is already complex for homogeneous graph, so it will be even more complex for heterogeneous graph. So we talk about to perform link prediction, we really need to split a graph into 4 categories of edges. They are the training message edges that are used to compute the embedding during training time. We then have additional training supervision edges that want to generate the objective for training. We then have a validation edge and test edge that are used for validation and test set as well. So there are 4 categories of edges for link prediction. And then in this heterogeneous graph scenario, we then have like for each relation type, we have these 4 categories of edges. So you can see that there are for each relation type, we have 4 set of edges, and they're associated together with their edge type. Question?
So do we always randomly split the edges into message edge or supervision edge, or it depends on the prediction task itself?
Mm-hmm. Yeah, good question. Yeah, how to split? Indeed, in most cases, we assume it to be randomly split. But suppose you have some a prior knowledge about how to split edges, you may want to do so. For example, let's say we have want to examine the out of distribution generation capability for a given model. Then we may want to manually select some out of distribution samples as the test set or validation set. But in most cases, we just randomly split. Question?
With the basis learning approach, it seems like you would really need to have a lot of different types of edges for that to make sense, because you're gonna, the basis needs to be a certain size or it's not gonna be useful. And I can't really think of real world graphs that would have many, many different types of edges like that. So I was wondering if you could give an example.
Yeah, good point. So earlier we have some example of heterogeneous graph. In theory, suppose we only have 2 node type edge types, there are 8 relation types, and suppose we have even like 10 node types and 10 edge types, then it could be 1,000 different relation types. So that's one way to understand, like there could be potential a lot of relation types. And another good example in practice is that like suppose we have heterogeneous information across different domains, and we still want to use one giant graph to capture everything we know. So we talk about this biomedical like knowledge graph, right? There are tons of different drugs and different patients, different molecules. In that case, you can easily define a lot of like types of nodes and type of edges in this application.
But even in those examples, not every edge type goes with every node type, right?
Yeah.
So it's not, doesn't really seem like it's actually combinatorial the way that you described. It seems like it's really more like linear in the number of edge types for a lot of these graphs.
Yeah, that is also fair. I think as I also mentioned, like some of the literature, they do not consider this relation type for the same reason you have described, because in a lot of real-world cases, like it's not really combinatorial. The edge type already clearly defined the relation type. But still, like first, in some cases, it could still be combinatorial, and in other cases, you can still define tons of different relation types. So these are some reasons we still want to like make the computation more tractable. Yeah, but great discussions. So we talk about the formulation of link prediction for heterogeneous graph, and let's see a concrete example. So for example, we want to predict this missing link from node E to node A, and this is for a particular edge type, relation type R3. So what we will do is that we want to get the embedding for node E and node A, and then we'll use this like a bilinear transformation to get the score for this particular missing edge. So we want to multiply this vector with the trainable weight matrix and then with another vector HA to get the prediction for this missing edge. So this is one way to construct the link prediction head for this heterogeneous graph. And then we want to outline the specific training and validation steps. Suppose you want to perform link prediction on heterogeneous graph. First, as we talk about, we can score all the potential supervision edges in the network. We talk about this from E, R3 to A is one particular tuple for the score, and we can use the same idea to score like all the supervision edges in the network. And the second step is to perform the negative sampling. So we didn't dive into details about negative sampling in link prediction earlier. It is a good time to discuss it now. So, so when we want to make link prediction, besides this so-called like a positive edges, because we know that there should be a link between this pair of nodes, we should also additionally consider negative edges. Otherwise, like the classification is like not well defined, right? We should both have positive examples and negative examples when we define a machine learning problem. And how do we generate these negative edges? One common way is to make the corruption of a ground truth positive edge. What I mean is that, for example, we know there's the ground truth connectivity between E and B. We could, E and A, and then we can consider corrupt the tail of this tuple to swap A with node B and D. And you can see that node B and E and D and E, these two edges are not existed in the network, right? So they are not existing in the network, so we treat them as negative examples. So we label this potential pair of nodes as negative. So this is the idea of negative sampling. So given a positive edge that we know, we want to corrupt it to some non-existent edges, and then this way we can get both positive examples and negative examples, and that can finish the setup of link prediction. And then we will also use GN model to score this negative edges. And how do we train the model? Well, we'll use the same standard binary cross entropy loss that we have also discussed earlier in the lecture. And our motivation is that we want to maximize the score of these training supervision edges that are positive, and then minimize the score of the negative edges that are want to minimize score for the negative edges. And this is kind of the loss function we want to optimize with. Question?
Yeah, for the previous slide, so the negative edges should not belong to the training method edges or the supervision edges.
Yes.
What happens if you have a really densely connected graph and that, like, you can't do that because they're all, like, the node, all of the edges that are possible on the edges?
Yeah, good point. Indeed, this is like a good, like a hypothetical example. Suppose the graph is already densely connected. I think in that case, actually, the link prediction problem is kind of ill-defined, because if the graph is already densely connected and there's no possibility of adding additional edges, then basically there's no way to infer additional links because it's already fully connected. But it's like a good example. So in that case, I think it is not very meaningful to define link prediction because graph is already densely connected. Yeah, but good question. Question?
So are we using like negative sampling for the negative edge, or should I just like choose it? I'm using another strategy.
I see. So the question is how to understand negative sampling and this negative edges? Is this the question? Yeah. Yeah. So that's a good point. So actually, I wouldn't think that these two notions are very correlated. So here, the idea of negative sampling, the negative edges is just to manually construct some of the edges that does not exist in the network. I think for negative sampling is like a more general strategy for training like a binary classification task where there are tons of negative examples and we want to sample some of them during the training.
So like, how do we choose this negative edge? Like when we are doing the training task, how do we choose that?
Yeah. So like we said, we want to corrupt given the ground truth, a positive edge, we can corrupt one side of the edge, and this way we can get the negative edge. Yeah. Okay, so we talk about having got the positive and negative edges, we can train the network to optimize this loss, or binary classification loss. And then at evaluation time, we want to evaluate how well the model can rank the edges with different relation types. So for example, now we have a new edge to predict over, pointing from E to D with the relation type R3. So to make such prediction, our intuition is that the score of E R3D should be higher than all the remaining negative edges that are not in the training message edges and training supervision edges. So this is what we hope the model will be able to see, to predict in this evaluation stage. So this is a specific metric that we want to report, let's say in this validation time. So first we'll calculate the score of this edge that we want to make the prediction from E R3 to D. And then we want to calculate the score of all the negative edges and use the same method we have just talked about. So we want to corrupt one side of the edges, and this way we can get the negative edges. So this way we can get a score for all the negative edges as well. And the third step is the most important thing here, that we want to obtain the ranking of the positive edge over all the negative edges. So this way we know that, for example, the model can rank the positive edge as the second among all the edges. And finally, we can report some ranking-based metrics like heat at k, which says that did we correctly rank the positive edge to be the first edge, and this a reciprocal rank tells us the reciprocal of the rank as well. So these are some standard ranking metrics for this problem. Question?
Back to 2 slides before this one. Just clarification question. In the loss function right there, that is indexed using the scoring function for R3. We need a summation outside of the to sum over all possible relations?
Yeah, that's a great point. Yeah, I believe here we only talk about one relation type, and you are right in the sense, suppose we want to get the final loss function, we need to sum over all the relation type. Yeah, this is just for one particular relation type. Yeah, good question. So, so now we have talk about how to evaluate like a link prediction problem for a heterogeneous graph. So the purpose of all of this discussion is also helping you get like a go over the idea of link prediction again. And we talk about something we haven't mentioned earlier about this ranking matrix. And this is just for your information of understanding, so it's not like the most important part of this lecture. And next, we're going to talk about a specific benchmark dataset, as I motivated earlier. That is widely used in the literature, and you could potentially consider in your course product as well. So this is called a Microsoft academic graph. It has like almost like around 1 million of paper nodes and around 1 million of author nodes. There are also institutions and fields of study nodes. So now we see there are 4 different node types in this particular graph. And then there are also 4 directed relationships between these node types. We have author affiliated with an institution, author writes a paper, and paper cites a paper, and paper has a topic or field of study. So there are 4 different edge types. And the prediction task here is to predict the value of a given paper. The features of different nodes are actually generated from the word-to-vec feature vector. So it's like a standard approach for natural language processing to get like easy to compute encoding for a given sentence or paragraph. And then given this feature we have for different types of nodes, we want to predict particularly for the paper node type and predicting the value of each paper. And it is regarded as a 349 classification because there are this number of values. Regarding data set split, I think student asked a great question, how to split data set. In this particular case, we do a time-based split. So it is no longer random split because we have this timestamp for all of these like occurrence of nodes and edges. So we want to respect that time when we construct the machine learning task. So during training time, we will select all the papers published between 2018 as training. All the things happen after that the year will be regarded as the test set. So this is kind of the machine learning setup for this Microsoft academic graph. So we can see some results on these benchmarks. You can actually log into the website of OGB, Open Graph Benchmark, to see more performance. You see that RGCN can generate reasonable prediction for this task, achieving about like a 47% accuracy. And then the state-of-the-art method is actually doing better. It is doing about like a 59% accuracy. And then the state-of-the-art method is actually a combination of complex and simplified GCN. Will actually cover both metrics in the later offerings of this course. So the discussion here is just to give you an intuition how people have applied this RGCN into a practical machine learning benchmark and how this benchmark looks like. So to summarize, we have talked about the major technical component of this lecture, which is RGCN. The idea is that we can assign different weight matrices for different types of relations, and this way we can extend GCN to relational GCN. And this method is pretty general. We can apply this to all the tasks we have seen for homogeneous graph as well, including node classification and link prediction. And this idea can be also extended to other types of GN. So we can apply the same idea to extend to graph stage, to GAT, etc. And we particularly, like I mentioned, the most widely used benchmark for heterogeneous graph and how it can be used in practice. Okay, so now we have talked about RGCN, the most easier to understand and also widely used method. Next, we're going to briefly talk about a recent state-of-the-art method called heterogeneous graph transformer. This is more for you to understand the research in this direction and see what are the interesting ideas to build heterogeneous GNN. So recall that we have introduced the idea of graph attention networks for homogeneous graph. And what is new or different from GAT to GCN is this trainable attention weight. So instead of always normalizing based on the node degree, we have a trainable attention weight computed from node embedding to let the model to weight different neighbors. So this is the idea of GAT. And our question that GAT is designed for homogeneous graph, can we extend it for heterogeneous graphs? So of course, what we have seen just now of RGCN, this idea RGCN can be extended to RGAT as well. So we basically define n different GAT models, each for one relation type, and we're then to extend the method. But this approach is actually very expensive because, as you can recall, the competition for attention is already very expensive. So we have separate branches of computing attention weights, and then attention weights usually is so-called multi-head attention. So we have to duplicate the weights for n times, k times, and then suppose with additional duplicate for each of the relation type is simply too expensive. So the question is, can we try to reduce the cost for this for heterogeneous graph attention? Another background that we want to cover here is about so-called scaled dot product attention, and this is essentially the attention mechanism that is used in the famous transformer architecture. So what we do here is that to compute the attention versus with respect to query Q, key K, and value V, we want to define this so-called scaled dot product. So we want to perform a dot product between the key and the values, and then scale it with the square root of the dimension, and then use that to weight the values V. So this is a kind of rough idea of scaled dot product. And then how do we obtain this Q, K, and V, right? So we don't have them in the raw input data. So usually what people do is to apply a linear layer to transform the same input to different matrices, Q, K, V. So we have the same input X to the network, and then we'll apply 3 different types of linear layer or transformation that can project this X either to Q, to K, or to V. So this way we can get the 3 component we need in this a scaled dot product attention. So now let's discuss how we can extend GAT to heterogeneous graph. We can see this. We'll kind of rephrase what we have for the GAT network. So we have the message function compute from each of the neighbors. We have an attention score that score tells us which message is more important. This attention score is also computed by a neural network. And after scale the messages, we'll perform an aggregation to get the final embedding. So this is the idea of standard GAT. And our key question I want to answer here is how can we make this attention to be specific to relation type? The relation type, as we know, have a tuple of node type, edge type, and node type into this attention computation. So this is the key we want to the key module we want to define for heterogeneous graph transformer. So this is the idea behind the HGT, heterogeneous graph transformer. We talk about the idea of projecting the input with Q linear to the query and K linear to the key. So in this idea of GAT, we want to decompose the tuple and try to project different components of this relation type, node type, edge type, node type, this tuple with different projections. And the purpose of doing so is that we want to reduce the number of weight matrices we can use here. So in this particular example, we have author node and paper node, two types of nodes, and right and side, so two types of edges. We have three different weight matrices that are used for the query paper, key paper, and key author, three weight matrices. And then we have two edge weight matrices, one for the side relationship and one for the right relationship. So altogether, we have 5 different weight matrices. Suppose we do not have this decomposition. So suppose we do not break down this relation type into node, edge, and node type. In theory, we could have like a 3 by 2 times 2 times 3, 18 number of different relation types, because we have this 3 node types, 2 edge types, and 3 node types. This number of weight matrices. So really, the idea of HGT is to decompose the tuple and model like each component of this node, edge, node relation type separately. And this way we can save the number of weight matrices we can use here. This is also like a glimpse of the exact formulation of HGT. It is also not the main focus of this lecture, but just for you to understand what people can do in practice. So we talk about this K-linear and Q-linear, which basically construct the key matrix and Q matrix that we talk about in this transformer-like attention network. And then after getting this Q and K, we then perform this so-called scaled dot product. So we make a dot product between the query and the key, but because we also additionally have the edge type between a pair of nodes, so there's a third trainable weight for each edge type, this W for edge type E. And this way we can get the attention score that we have seen earlier also in the standard transformer like attention. So this is kind of the idea of HGT in terms of computing the attention weights, but then with respect to the relation type. And then a full HGT layer would look like this. So we talk about, we have the attention weights to weight different messages, and we have just computed how to score like a given message based on the relation type. We have just seen this. Similarly, we can compute the message with respect to different relation type. And here we also follow the similar idea of decomposing the weights for node and edge types. So to compute a given message, we have the weights for each node type. So given a node, we will get its node type and then apply a message transformation for this particular node type. And then we will multiply this node type like messages with weight matrix for each edge type. So you see that instead of we model for this each particular relation type, so we have the number of relation type of number of weights, we now decompose into the weights for node type and the weights for edge type. So now we have a summation of number of node types and number of edge types, this number of weight matrices. So we reduce the number of weight matrices we want to use here. There's a question?
Just a question about notation. Can you explain what the symbol circle with the cross in means?
You mean this one?
Oh no, I'm sorry, at the very top.
Oh, this one? Yeah, that's a good question. I assume this should be summation, but I need to check offline as well. But my understanding this should be something similar to summation because we have get the weighted message, right? So, and we want to sum over the neighbors of a given node. So it's most likely to be a summation. Question?
Or is it just custom aggregation function.
Oh yeah, yeah. I think that's exactly what is supposed to mean. So summation is just one option. This notation means in any possible aggregation function. Yeah. Thanks for that. Question?
Can you explain why just the attention weights aren't enough to distinguish? Like if the attention is different weights for different pairs, wouldn't that be enough to capture like different relation types?
Yeah, that's a great point. So I think this can be understood as the motivation of GAT, right? The whole purpose of GAT that extend GCN is to introduce like a trainable attention weights for different messages, but still we have to compute the messages for example, we have author node and paper nodes. We want to construct separate messages for each author and each paper. So we just additionally learn like a attention weight to score these messages, but still we want to differentiate these two types of messages. So suppose we do not consider types for like these messages, then we kind of lose a lot of information by sharing the weights across types. But that's a great question, yeah. So we have finished the discussion of GAT, HGT, which is a widely used like a attention-based method for heterogeneous graphs. We can also take a look at how HGT performs on this Microsoft Academic Graph dataset. Very interestingly, we find that HGT use much fewer parameters, and this is as expected because now we have decomposed the weight matrix with respect to each node type and each edge type. So it saves a lot of parameter compared using RGCN. Like it almost reduced by a number of magnitude, by an order of magnitude. And in the meantime, it performs better than RGCN. So kind of this is like an illustration why HGT may be more desirable in real-world applications. So in the remaining of this lecture, I just want to briefly discuss how we can extend what we have learned from the design space of GN to this heterogeneous graph scenarios. So remember we talked about these 5 components that outline the general perspective of GN for homogeneous graph. And our question is that can we extend this framework to heterogeneous graph as well? So recall that the first component we'll talk about is the message computation, compute a message from each of the neighbors of a given node. In the case of heterogeneous graph, we talk about this idea of defining like a one particular message function for each relation type. So now the message function will have a subscript of R that represent like a a specific function for each basically relation type. And this discussion here is useful because we talk about we can model this message function arbitrarily. So in RGCN, we talk about just a linear layer as the message function. In practice, this message function can also be very complex. Can even be like a 2-layer MLP or even more complex. So we can still follow the same idea. So we define a different message function for a different relation type. And then we talk about the formulation of aggregation that aggregate the messages of a given node. And in the language of heterogeneous graph, now the aggregation will be a 2-stage process. We also briefly touched it in RGCN. So here are the 2 stages. The first stage of aggregation will aggregate the message within each relation type because, for example, for a given relation type, we may have different members that belongs to this relation type. And having aggregated over the relation type, we may want to additionally aggregate over all the relation types because now we have information obtained from each relation type. And one particular example I would recommend you can consider to use is that in the first stage, we can use the sum aggregation over the members of a given relation type. We talk about sum aggregation is the most theoretically expressive method in this series of GN that lecture. So we can first take a summation for each relation type, and then we can take a concatenation across the relation type. The purpose of using concatenation is that now we do not have to consider the permutation invariant property, right? Because let's say we have defined 5 different relation types. They are clearly defined. So these 5 relation types are explicit, and we do not have to consider the ordering here. So concatenation is kind of the most expressive way that we can keep everything we have learned for this 5 relation type. So the second aggregation could be the concat function. And we talk about the connectivities between GN layers, including adding the pre-process layer, post-process layer, and skip connections. And for heterogeneous GN, we can basically keep the same design for the homogeneous graph. The only thing we can discuss is that for those pre-process layer and post-process layers, we have this so-called MLP layers. And now these MLP layers should be with respect to each node type. The reason is that the output of any GN layer are node embeddings. And because we have potentially multiple node types, we want to separately transform the embeddings of nodes that belongs to different node types. So now the MLP here should also be type sensitive. So this is how we can extend this pre-process and post-process layers for general heterogeneous GN. And lastly, we'll talk about different ways of augmenting the graphs. Like we talk about how to add a feature for nodes and add a structural information for heterogeneous graphs. And most of them are state unchanged, except that we want to discuss 2 common options when we want to generalize the approach from homogeneous graph to heterogeneous graph. So there are basically 2 ideas. The first idea is that we want to compute the statistics within each relation type. So we talk about the analogy of a heterogeneous graph can be regarded as n different separate graphs. So we can compute the statistics or perform the subgraph sampling for each of these a relation type. And another approach is basically we just ignore the relation type. So we treat the heterogeneous graph as a homogeneous graph without any type information. And then we can compute the graph statistics or perform sampling over the entire network. So finally, regarding different prediction types, we have visited node, edge, and graph level predictions for homogeneous graph. And similarly for heterogeneous graphs, we just need to consider this relation type R for these different prediction types. So now we have seen that we can extend the idea of GN from homogeneous graph to heterogeneous graph. And all we need is to properly consider this node and relation type and have some additional 1 layer of aggregation over the relation type. And that is all we need to make such extension. So to summarize today, we have talked about how to apply GN to heterogeneous graph. And the key concept you can take away is this concept of relation type from the starting node, edge, and end node that describe all the complex relationships in heterogeneous graphs. And we talk about the idea of learning from heterogeneous graph using the same idea of GN we have seen earlier. And the key idea is that we want to separately model each relation type with GN. And the most important part of this lecture is relational GCN that extend GCN to relational graph. And that's it for today.